Welcome back. Today we're going to talk about vectors. Now I can't hear you from where I am up here, but in my normal classroom, as soon as I said we're going to talk about vectors, I would hear a lot of oohs and ahs coming. And I don't know if those are all the people that hated vectors when they were in physics class or not, but it seems to me like that seems to be something that people just don't like very much. I'll try to make it a little more applicable to you this morning. Let's take a look a little bit at a couple of things here. Uses of vectors. If you are into any kind of video games, maybe you have an interest in moving into that area sometime as some sort of a designer or programmer. Vectors are usually used to communicate relationships of objects in space. That's what we do with them. But they can also be used to move objects like players or even projectiles around in a video game. Vector math could be tedious by hand if you had to do those kind of calculations, but of course computers are great at making a lot of iterations, and so computers are really good for that. You know, if you have an interest in that, here is a book that's one of the classic books out there on graphics and game development. It's a 3D math primer because 3D seems to be the ways that we're headed right now. And if you were to pick up that book and look at it, you would find that there are 3 chapters in that book that are devoted to nothing other than vectors. Now, we wouldn't cover the simple 3D vector class much in here, but we would be doing everything that's basically in their chapter 4 and 5. So if you're going to learn anything about vectors that way, this might be a useful thing to you. Here's another possibility. If you have an interest in climbing, this video that I'm going to give you a link to here actually shows a couple of people, and I'm not sure they're young people. I know it's subtitled, that I don't know really what country that they're coming from that much. I could probably figure it out from the web address here. But they talk a lot about vectors in climbing. When you put your foot in a certain spot, how much of your force is going against the hill, how much of your force is going down. And that helps determine whether you're going to have a good spot to place that foot or not. So if you want to take and stop the video or stop this lesson at this time and go ahead and look at that video, I think it's about 10 minutes or so, you could actually see some application of vectors in the climbing mode. Now, you probably recognize that the picture on the right doesn't look like it's real clear. Well, these images that you see on the left is called a raster image, or sometimes called a bitmap image, made up of thousands, millions of little pixels. And when you try to take and enlarge it, it kind of gets blurry as you start seeing all the little pixels that might be there. Well, not so the problem if you save something as a vector image. Vectors are used in this. Now, I don't know if this was done using Photoshop. My guess is it's a program similar to that. But we take the hot air balloon there, and instead of storing it as a series of pixels, we store it as a series of lines and curves. We store it as a vector image so that now when we enlarge it, we don't lose any of that detail that we had before. If we would have just enlarged that as pixels, that's the same thing we'd be seeing there. So vectors can be very, very handy when you do there. How about not just looking at the image, how about storing them on your camera or storing them in your computer? You probably know that if you have lots and lots of digital photos, they take up a fair amount of memory in your camera or your computer. If you reduce the size of the image to make it take up less space, then of course you reduce the size of the image and it's smaller than it was before. On the other hand, if you store something as a vector image, it has the same small file size no matter what the image size is. This is because the image is being stored again as a series of lines and curves. If you stored a raster image, every pixel needed to be stored, and that's a pretty inefficient way of doing it. So when you just think vectors are little arrows that you play with in physics class, understand that vectors are important in a lot of areas. And so we want to do that. So some basics that you may have covered before. Again, we'll do a separate little problem section on this when we get done. Scalars and vectors. Scalars have size only. It wouldn't make a whole lot of sense to talk about the direction of a temperature, the direction of a surface area, because there really isn't a direction there. Magnitude only. Whereas vectors also have a direction. Force goes a certain direction. Velocity goes a certain direction. Acceleration. Now we're doing math angles here to start with, so we measure counterclockwise from the right, just like we did in the unit circle. So we take a look and see. All right, more things about vectors. Even though vectors are represented by an arrow, they are not rays. In geometry class, anything that had a solid point on one end and an arrow on the other meant it started there and went on forever. That's not true. When you're talking about vectors, vector PQ starts at P, ends at Q. Now my arrow goes a little bit further than that because I couldn't get Q placed exactly where I wanted to have it, but that's what's true here. Vector PQ means starts at P, that's called the initial point, ends at Q, terminal point. Now, sometimes vectors are going to be named with just one letter. In this case, a little arrow over the top of it, small letter, vector V. Length of a vector. Now, when I use the length of a vector, I use a double set of vertical parallel lines on either side of the vector. Now, some books only use one set of vertical lines as shown in the second thing there. Now, the reason I normally use two is so that we're not really thinking, oh, it's the absolute value. It is like the absolute value in that it's the length value, and lengths are positive, so you can think of it that way. But whatever your book uses there is fine with me. That's not going to make a whole lot of difference to us. This one's a little tougher for people to understand. Equal vectors don't have to be in the same place. They don't have to be on top of each other. They just have to have the same size and the same direction. So those two vectors there, which are both going exactly the same direction and have exactly the same length, are equal vectors, even though one is considerably away from the other one there. So, adding vectors. We want to add the vectors head to tail. There's a lot of methods out there that people use. Head to tail is usually the one that I found that students have less trouble with. I taught high school for many years, and I know the problem areas that students have. And in adding vectors, if you can always get them to go head to tail, seem to be more successful when they get done. So when you do that, when it says adding them together, it doesn't mean adding their lengths together unless they happen to be in a straight line with each other. It means figuring out where you would be if you started at the tail of one and ended at the head of the other one after you put them head to tail. The resultant is basically where are you compared to where you started. So that shown there in the dashed line in black is the resultant of adding V and W together. If vectors aren't in the same place, like those were, move either one of them. So if you have these two vectors that are sitting like this, and you want to add them together, move one of them. Now if you look at the top drawing, that is the result of moving vector W up and putting it at the head of vector V. Putting the tail of W at the head of vector V. That's how I was able to add them together and come up with the resultant there. Okay. So what if we want to add these things together? Well, most of this is trying to figure out exactly what somebody's talking about. It says add PQ, QR, and RS together. How do you get PS? Well, if you think about it, PQ means you went from P to Q. And then add that to what happens when you go from Q to R, and then you went from R to S. Well, if you go from P to Q to R to S, you ended up starting at P and ending at S. And so we've got the vector that's PS when you get through with that. So let's look at the easiest case possible of adding vectors together. What if they're in a straight line? Here we have a couple of vectors both going to the right. Pretty easy to add them together. Here we have one going to the right, one going to the left. And so you end up with the difference of those two. 5 and -2 ends up with a length of 3 still going to the right. I don't think that needs much more explanation than that. But that's the easiest case. And you should always check and see if it actually is the easiest case. Some people want to apply a formula to everything without actually looking at it. So look at it and see. Next case, what if they're at right angles to each other? Well, we of course got to move one. Got to make sure we get head to tail. Then, because it is a right triangle that we've created, so here's a couple of vectors that we have there. We could move either one of them. We'll see that on this next slide here. I'm going to take and move the 5 one to where I put its tail right at the head of the 4 vector. And when I have that there, then I now have a right triangle. And I can take and solve using the Pythagorean theorem for the length of r. And then I can also take and use inverse tangent to find the angle theta. I don't think we need to stop and do that right now, but instructors, remember, it's your call. You always get to decide when to stop and have somebody do something. Last case, vectors are not at right angles to each other. One way is to move either one of them to create a head-to-tail relationship and use what you know about parallel lines to create a triangle. Then solve the triangle using law of sines and or the law of cosines. Usually it takes both, depending on how much information you need to have. So let's see what we've got. We've got 2, maybe forces here that are acting on the same object. One pulling to the right with a value of 10, one pulling up at an angle of 80 degrees with a value of 6. Now you can't just take and add these together unless you create either a parallelogram or you somehow create head to tail. Now it's basically doing the same thing. So when I take this one, this 6, and move it over here, and I want to take and connect that, then I actually have a way to do this. But I got to understand some things about parallel lines. One of the theorems that you had was if a transversal cuts a pair of parallel lines, the interior angles on the same side of the transversal are supplementary to each other. So if you have an 80-degree angle here, let's see if I can't get that there a little bit. If you've got this 80-degree angle here, then this angle over here must be supplementary to 80 degrees, which now we can put in as 100 degrees. Well, once we have that in, we now have a triangle. It's not a right triangle, but it is a triangle that we can solve. It is a triangle that because of having an angle sandwich, we can certainly use law of cosines to find the resultant length. And then once we had that, we could use law of sines in order to find angle theta. So it certainly is possible for us to figure that out with the things that we've learned so far. Now, let's consider a problem. And the problem we're going to consider looks like this. Vector v has a magnitude of 100 units at an angle of 45 degrees. Vector w has a magnitude of 100 units at an angle of 80 degrees. Find the resultant when the two vectors are added together. Well, the first thing I would do is say, all right, let's take and do this. And putting the tail of one to the head of the other one, let's do this. Let's let vector v be the one that we draw first. And at the head of vector v, let's draw vector w. So take a couple of minutes and actually do that. And let's see what your drawing looks like. Okay. Now, Let's see if our drawing looks like that to start out with. So what I've done is I've taken and drawn the vector there at 45 degrees, length of 100. And then I think the biggest hint that you come up with here is when you're going to put your second vector there, put on a second little set of axes. You can make them light, pencil, dashed, whatever you want to do, but I think it's really important for you to take and create that second set. Because most of what we have to do now here is figure out from this, what is the size of this angle right here. If we can find the size of that angle in the triangle, we can solve this triangle because we have two sides. We have a 100 and we have a 100. If we knew that angle in between them, we could use law of cosines and find the length of r. And of course, as I said before, we could then go on from that and use law of sines to go farther. So let's talk about that. I think this is a point where your instructor really needs to help you look at things in terms of solving for the size of that angle. Now, it may not be all that hard for you to do, but see if that's something that you can do at this time. I'm going to tell you, the big angle in this triangle is 100 degrees plus 45 is 145. Now you need to think about where that came from. So I'm leading you to the answer, but you need to think about where that came from. All right, my suggestion to you, if you're having trouble seeing it, is redraw your first vector, the one at 45 degrees, and the second set of axes, and don't draw anything else. And think about what we called in geometry alternate interior angles. If you'll do that, you probably could figure out that this little part right here, this little section right here, is also 45 degrees. The rest of it's pretty easy to come up with because you then see a square angle, a right angle of 90, and you know what's left out of 90 from the 80 is 10. So if you go 10 and 90 and 45, we come up with our 145. So now that we've talked about how that came up with, and that's why I have you draw that second set of axes there. Now that you do that, talk in your class about, is there a rule there? And would that rule hold for all vector pairs? In other words, what if we had taken this and instead of that second vector going that way, what if that second vector would have gone this direction? Would we have done the same thing? What if that second vector would have come down to the left or down to the right? Would we have done the same thing? I think those are critical ideas that will help you to solve any of these triangles. So I want you to talk about those in groups or talk about it, as a class with your instructor and see if there is some general rule that you can come up with there. Okay, now that you've talked about that, let's take and do this. Finish solving the triangle. We know that we've got an angle of 145 degrees and two sides of 100. Solve the triangle for the length of r. And once you've solved the triangle for the length of r, then go ahead and find your angle theta that is indicated there. All right. If your math agrees with mine, we use the law of cosines in order to find the length of r. And we got a length of 190.74. And then using the law of sines to solve for angle theta, we got angle theta is equal to 17.5 degrees. Now in this case, I'm not too worried about checking to see if there's another angle that has that same size, because if we took 180 minus that and got 162.5, And we're already having a 145-degree angle there, I don't think that's going to be possible. So I know that's the size of angle theta. Here's a problem many students have. They stop right there. Hey, I found the angle. It's 17.5. Yes, it is. But our angle is measured up from the horizontal. So we have to remember to add 45 degrees to that in this particular problem and come up with an answer of 62.5 degrees. Well, that's not too bad. And once you learn kind of a pattern there, it's not too bad to do with all those little things. And it's not hard at all. There was the ones that we did. Didn't seem too bad to take and do that, moving one and making a triangle and do it. But let's imagine something for a minute. Let's imagine a real life situation. And in real life, there's not usually just two forces that are acting on something. There's usually more than that. It's kind of like the difference between whether you like fractions or not. Can't we just do it with decimals and whole numbers? Well, in real life, there are things that are fractions. You have to learn to deal with those other things. So think about what you would need to do in order to take and add these four vectors together. Now you could take that and say, well, I'm going to get out a piece of graph paper. Okay, that'd work. How good are you with that? If you're really good, you got a protractor that you trust completely. You can make your lines exactly the length that you want to make them and drawn to scale, and you can put in vector A and then vector B and vector C and vector D, and then you can measure the resultant and measure the angle. You could do that. I don't think it's going to be very fast. But on the other hand, I don't think the method we just used is going to be very fast either. For just two vectors, it may be as quick as anything you can do. But for four vectors, you'd have to add A and B together and figure out that resultant and what the angles were, and then you'd have to add that resultant with C, then you'd have to add the resultant of that with D, and if you made a whole bunch of axes, maybe it could work. So when I tell you there's another way to do this, understand that it's not necessarily faster for two vectors, but for more than two vectors, it's about the only way that you want to do it. The easier way is called resolving the vectors into components. So when we do this, we're going to take, in every vector that's going at an angle, has a horizontal part that made it up and a vertical part. So we're going to split it into those horizontal and vertical parts. You already know how to do this because you already know how to use sine and cosine. We're going to resolve each vector into its horizontal and vertical components, x and y. And we're going to use these facts that we know. If that blue line up there is the radius, and in the unit circle, that's exactly what it was. It was the radius of the circle. We know that cosine is x over r and sine is y over r. But that's not the form we're going to use them in. We're going to use them in this form. Multiply both sides by r. X equals r cosine theta. Y equals r sine theta. If you memorize things, do it. I mean, this is something that's way too easy to not memorize. If you want the x value, it's r cosine theta. If you want the y value, it's r sine theta. X is r cosine theta, y is r sine theta. Say that over and over enough times and you'll get it. So if we have the vector v, and notice I put a subscript x under it there, the x part of that vector is 100 cosine 45. And the y part is 100 sine 45. For the other vector, the x part that's there, if we took a look at this, the x part would be, whoops, this part coming right to there, and the y part would be that part right there. So the x part is how far did you go horizontally? What was your value of horizontal? What was your value vertically? We do that with both those things. So this one has it drawn without me doing it freehand. Looks a little bit better. The x part, r cosine theta. Y part, r sine theta. So when we've got that done, we know what we're dealing with there. All right? So when we've got that finished, what we can do is really simple. It's really, really simple. Once you find v sub x and w sub x, let's take a look at that. Okay? There's v sub x. You can find that, 100 cosine 45. And you can find this one over here, 100 sine 45. Well, those are two vectors in the same direction. We learned the easy case, when things are in the same direction, we can just take and add them up. So our total horizontal component will be 100 cosine 45 plus 100 cosine 80. We'll do the same thing for the vertical components. If you look at the vertical components here, and we've got this vertical component here, w sub y and v sub y. If we know those numbers, they're both adding together in a straight line this time. So we can find the total in the y direction by just simply adding those two numbers together. So there's our total in the x direction. 100 cosine 45 plus 100 cosine 80. You can work out the number, or you can simply just leave it like it sits right now. There's our y. I tried to draw them as close as I could to scale here, but that one is 100 sine 45 and 100 sine 80. Now go ahead and work those two numbers out just to see if you like doing that. Get those two numbers and see what you can do. All right, if we solve for the x1 and the y1, we should get an x component of 88.08 and a y component of 169.19. Now, if you're not noticing things, we didn't have to draw any other set of things. And think, what if we'd had 6 vectors? Every single one of them would have been r cosine theta plus r cosine theta plus r cosine theta, all 6 x components together and all 6 y components together. So when we get done, we've got 2 numbers here, and the resultant is still the diagonal between those two. So if we take a look at our resultant here, we've got a right triangle. Not only that, angle theta is our actual angle of travel. So we're able to solve Pythagorean theorem does work in a right triangle. So we can square those values and do the square root of those. We can actually take and find the angle using inverse tangent. So go ahead and do that, and then we'll check your final answer in about 2 seconds. Those are the numbers that you should have come up with if everybody's math is correct, including mine. So that's the basic run-through of vectors. You know, we don't have any problems in this section. We're going to do those a little bit separately with the problems on log sines and log cosines. And we have one more section that deals with vectors, and that's the algebra of vectors that we will do in another lesson. Thank you.